Okay, you're all set?
What?
Ready to start.
Ok, bueno, pues hola a todos. Bueno, pues que parece que es la recta final. Yo solamente voy a presentar algunos casos que está implementado en WebGS. Bueno, parece que Lionel me dijo de hacerlo en inglés, así que voy a hacer un switch. Bueno, pues que I present myself. My name is Guilaume Morvan. I'm a French engineer. I'm working in Lagos, actually, with Rashid, Lionel, but also Patrick. You will see tomorrow. I will. No, sorry. I'm working with modeling research people. I designed and I configured some configuration with Nemo, but also with CROCO. Now I will show you some test cases I did in the last 2 years related to USGS. And yes, maybe that's it. So, sorry, I will shut off the stack. Okay, so first of all, for the motivation, what does it mean? Okay, sediment test cases. The fact is here is to isolate specific sediment processes and to use it with, you know, with cheap cases, low computational cost, to isolate processes, or to isolate also new method or new scheme for interpolation, for instance, for the bed load. It's interesting also to initiate some comparison. For instance, I did some comparison with the Mustang, with the same case, and we interact with people with who are working with Mustang and the other model, and we try to converge with a solution, and it permits to see some processes which are present within each model as it is written, and to see different schemes implemented, different vertical grid management, and that's it. The thing is it's interesting to share experience and to know shortcomings of each model. Rashid already talked about CROCO and the code using CROCO. So rapidly, you have USGS, the native one, from UCLA community, and the French model from French Institute Ifremer. So it's a mud and transport modeling. I also put the name of people if you have some question. Yeah. So okay, so I go quickly. I will begin with Dune test cases. So I will try to do it step by step, like a beginner. So to begin, on the right, you have the CPPDF file here for the Dune test case. With also, you have sub cases here called as AnaDune and Dune 3D. The purpose here is to test the capacity of the model to simulate well the migration of a dune. Here we have a bedload process only. There is also a goal is to see if the model shape will fit well with steeper slopes, and also to know about stratigraphy, to know how the sediments are sorted as long as the dune evolves with time of simulation. And sorry, Okay, and subcases. There is one. Andres. Okay, I think there was a problem. Okay, so subcases are Dune 3D, so it's the same. So in 3D, I put it the iframe name, so channel test cases. It was implemented also with Dune and during the implementation of Mustang. We also use Dune, so it's an analytical case from a thesis from Mario 2007. And the goal here is to compare the numeric solution with analytical solution of a new bed load transport equation. And that's it. So Dune. I put a scheme on the right. So it's a scheme, it's a simple channel with a dune of 2 meters. This is 100 meters long with this dune is at the middle. So it's a physical point of view. If you look at the model point of view here, it is extracted from the routine of sediment of USGS. So as we can see, is the model point of view for this case will give you explain that we are using 20 layers on the seawater. So I put it to know how does it work the index. So the first one begin at the bathymetry and so on. And for the sediment, you go upside down. You have the first here just below the bathymetry and so on till the bottom of the sediment bed. Okay, and I noticed also that for Mustang model, yes, we have a different management of index on the vertical grid. So it's upside down. You have one to the bottom of sediment, and the last one is just below. Before I said, or Rashid also said, that I don't speak about Mustang, but it just to have to keep in mind this if you want to analyze this output of Mustang, you have it's important. Okay, to speak about the dynamics, what happened? It's just a channel, so and you have a barotropic flow. We flow on 0.6 meters per second. 6, sorry. We use vertical mixing of GLS. We also activate the morphodynamics. And we use bottom roughness length called like ZOB. There are many ways to estimate this term. I put it just to, it's important because it's a key parameter when you process bed load. And it is on the name list of CROCO. Normally you already know. It's called ZOB. And you are 10 power -4. It's important because when you change this parameter, you will change also the U star and then the bottom stress. So it's a very sensitive parameter. This is for CROCO, and now for the sediment, as Rashid talked about the name list of sediment. And also this file, sediment Dune.in, is on the test case directory as the same with the other test cases. And Okay, so I try to explain like Rashid. Here we have two lines, which means that we have two different classes, one for 600 micrometer, 255 micrometer. So one is coarser than the other. We have density here for the standard density, and also a key parameter for each class. We have the critical shear stress for erosion. As Rashid said, is a threshold of that initiates the motion of sediment. Also, we have this is a fraction of each grain size on each layer. That means that we have 50% of each sediment on each layer. And we have here is meaning that we have 10 layers of 30 centimeters. That means we have 3 meters of sediment. Okay, so porosity is standard 0.4. We don't use this for ripple process. We don't use it. And bed load coefficient, there is no differences, and here no factor to diminish or to increase the bed load. And the move of the dune also, there is one. Okay, so as I said, we only use bed load. So here we are using the bedload formulation from Woolin 2014 with the slope effect from Lesser. So I put here it just for the CPPDF file. It is defined by default here. So as a result, we have 10 layers of sediment here. So in red you have the bed position, so at the beginning, and the thing is to see what happened next 2 days of simulation. What about the color? So green mean that we have at the beginning, like it is written on the sediment file, is 50%, okay, and then here as on the front of Dune, here we have different colors. So blue means that we have coarser sediment, and just below it's contrary, it's a finer sediment. Okay, and we also see that the front of Dune move for even more 10 meters, maybe 15 meters. So what is for the dune by default? We have also as a dune the same for three dimension. There is only just another direction, and the same way we see the result of the bed, when how the bed is moving at today, and that's it. We also have, if you define the CPP key and a dune, we can activate the analytical case. So as I said, it's from Marieux. So the goal here is to see if CROCO fit well with analytical solution from Marieux, and to test some different flux interpretation method for bed load when it remains analytical steep slopes. And in this scheme, we will see later that we have a steep slope. For the grid, so it's slightly the same for the dune by default. It's a ×2. We have 300 meter, resolution 2 meter. It's the same, but it's the same than dune by default, but by 2. And for the dynamics, the same, 2 times dune by default, and we are using the same parameters, ZOB, and the bottom roughness length the same. And for the sediment part, so as you know now, there is a other file and a Dune. So here we just use one sediment class, so 250 micrometer. We have the same with Dune by default. You are using 3 meters of sediment. And we activate the new formulation from Marieux with this CPPT. This is the formula. The formula of bed load. So there is some parameters here, but also the current. I put in black here for numerical solution. It's for the next slide, because for a numerical solution here we are using. So when I mean numerical solution, I'm talking about the CROCO simulation. So here we are with CROCO simulation. We are using the barotropic current, and for analytical solution we use analytical parameter like channel flow 10 meters square per second and the depth. So using a rigid there's a way. Sorry for the bug. Okay. Okay. I mean, okay. That's the result. So in black solid line, we have the numerical solution, and red the analytical solution. So as I said, we have steep slope for the analytical solution for Marieux. Here, the thing is to see what we have like differences if we are using first order interpolation flux like UP1 or fifth order interpolation flux as called WENO 5. With a quick look, we see that with first order it's smoother. The result from CROCO, and if we are using the other solution from WENO 5, we see that it gets closer to the steep, and it fit better than the first order. So there is an important a good way to see which method to interpolate is good or not. If you want to process some configuration with it. I go quickly for set toy. So this is a set toy family test cases. This is another one. Now we don't talk about. It's not a channel. We are not using bed load. It's much more one column of water. We are using suspended load only. We have a flat bottom. So it's interesting because it's a ship case. We can use it to isolate some processes, as Rashid said, with non-cohesive and cohesive sediment, to study erosion, deposition, consolidation, but also flocculation. And we can have sub-cases. It's called like a CPPT from rules. Rules, it means this is a case implemented, it's come from Ifremer, is to see if a numerical solution from CROCO fit well with the rules theory. We also see another case like a resuspension event. So we have two stress events with erosion and resuspended resuspension of material. And the other one is to study consolidation. So it's here. And these two are coming from the paper from Sherwood. So I invite you if you want to have more information about it. So COAST, that means that it's couple, ocean, atmosphere, wave, sediment system. And that's it. So I begin with the rules subcase. Okay, so you can switch this with this flag on the set.cppdef file. And okay, so what happened here? We give to CROCO 100 layer of column water with 5 meter depth. So we have a resolution of 5 centimeters. And we have 1 layer of sediment of 10 centimeters. So you see it here, as you know now, on the part, the thickness part here. And okay, and also and the dynamic. Okay, so we are using only vertical movement. It's a background vertical viscosity. It's a constant. So for the sediment corresponding to the file, we see that we are using cohesive sediment here, and we are using in the column here an initial concentration of CO2. Each mud class have a different settling velocity here, and we are using the same erosion rate. And we want to see what if the model fit with the theory of Roos. Quickly, I only said that when you have suspended sediment, behave like a tracer. We can treat it like a diffusion problem with higher concentration at bed and lower close to the surface. So we have a Roos theory here. So it's linear in depth with the initial concentration and the depth. It's the total concentration, sorry, the total height of the column of water. And associated on this, you have a Roos number. So is a ratio of the settling velocity with the shear stress velocity. And you can compute an analytical concentration based on this Roos number. What does it mean? It means that if you want to know if CROCO fit well with Roos theory, you have to compare these two profiles. So that's it. So on the left, we have lower settling velocity, and on the right, you have higher settling velocity. That means we are the first sediment class, the first mud class and the last mud class. What we see that we are not, so we are comparing the USGS, so the CROCO solution with the Roos theory. We have the column of water here. So we have 5 meters, and we compare the concentration ratio with the concentration at the surface. And the first thing we see that it's fit well, or more or less well, with the theory of Roos. As we can see, when we have a lower Roos number, and this is the case because we are with lower settling velocity, it's intuitive, we have higher suspended sediment on the field. Because with lower velocity, you imagine we have more sediment remain on the feed. And the other part, so with mud class with higher settling velocity, we have higher Roux number, and so a lower suspended sediment on the feed. So I move on the next case from Sectoy. The idea here is to demonstrate the evolution of stratigraphy caused by multiple erosion or suspension events. So the thing is, we have the same. No, I don't think it's the same. No, we have 20 layers here on 20 meter depth, so resolution 1 meter. We are using 4 centimeter depth of sediment. And to go back to the goal, to the purpose of this test case is to see on the dynamic what happened. Here we are using two events of wind stress, which is applied on the surface and that generated horizontal velocities on the column, and that generate bottom stress. So that is on the right. You see the first event. So you have 5 days of simulation. You have the first event, the 0 to 2 day. You have the first event. It's a bottom stress of 1 Pascal. At 1 day 7, we stop it, and again we put again another stress event at the half magnitude, 0.5 Pascal, and we stop it again at 4. So what does it mean? Sorry. Before I only talk about the classes remain here on the bed sediment. So we are using here non-cohesive and cohesive sediment. So the first line here mean that we are using same classes, and the 2 line here mean that we are using mud. We have also different settling velocity, as you can see, and also different critical shear stress for erosion. So I will try to do it slowly. What happens if we have 2 events of stress? So on the top, you have the water. You can imagine it's water. It's mainly the concentration of each sediment on the water. You have here, we are going the same. We are going to 0 to 5 days of simulation, and color we have blue and red one is for non-cohesive sediment, and the yellow and purple is for cohesive sediment. So what happened? What happened for this case? So at the beginning on 0, we have below the bed sediment layer. So we have equal fraction of each sediment on all the sediment. So here you have 0 to -4 centimeters. Okay, so what happened when we apply the first stress event? We are going to erode, and that means that if you look on the right, it's the result of the stratigraphy 2 days later. We have a change beginning at 1.2. We have a change of fraction of each sediment. That means that here we have all of this material is going on the water. So you can see here we have different classes. The concentration is increasing. We have more we have more so cohesive sediment here, much more than non-cohesive. And what happened 2 days later? So here we see that 2 days later, 2 days, I remind you that we stop the bottom stress event here, and the coarser sediment begin to deposit. So here you have much more non-cohesive sediment here. Okay, and also I put on C. It's between the two times at 2 days we have a net erosion of 0.8 centimeter. So what happened next? So we don't have any more stress at on the bottom stress event, and at 5 days. So next, the second one, bottom stress. We see that here on the stratigraphy, we don't have much more non-cohesive sediment, and it begin to deposit erosion, mud classes erode here, and it's remained on the column of water also. And also we can use we can see that we have a net erosion between the beginning of 0 and the last. At 5 days, we have a net erosion of 0.2 centimeter. I will talk about this. This test case is slightly the same of the previous one in terms of grade, in terms of sediment. But we want to study to see much more the consolidation processes. I think Rachid talked about that before, but I will try to do it to explain what happened here. Okay, so the goal, what is it? Is to see the cohesive behavior due to a single bottom stress event, and to show consolidation and swelling processes. The key thing is to keep in mind that sediments do not erode in the same way, depending if you are considering cohesive sediment or not. And as Rachid said, that erodibility becomes a property of the bed layer, and not you don't have erodibility for each class. So you have a critical shear stress for the erosion to each layer in the bed of sediment, which is increasing with depth. And to modelize this, it is implemented within USGS using a cohesive bed module. So a little bit complicated, and Rachid already talked about this, but okay. In this scheme, as you already see, we have different, we have an initialization by the cohesive bed module with a global critical shear stress at equilibrium. And you give some parameters, time scale for consolidation or for swelling. This is to accelerate or not each process. So this parameter you have to fill in to fill it on the name list of sediment we will see later. What does it mean? It means that if we are applying a bottom stress, then we will have changes on the erosion profile for each layer. And depending on what time scale you are using, there will be like a nudging of profile to the equilibrium profile here. And that means that depending on which part you are on this scheme, your bed will be more erodible or not. Here on the right, you see the name list for consolidation. So the most important it's below. I put here, it's the parameter we give to USGS, to the cohesive bed module. So we activate this module and this cohesive behavior given a threshold value trans n, which is fraction depending of the fraction of mud you have on your bed. And if it is above this threshold value, then the cohesive bed module will consider it with behavior, with cohesive behavior. And so you have also another parameters for slope or offset. This is to compute the equilibrium profile you see before. And the time scale I was talking is the time scale for consolidation. So it's a tercetim here. So it is in second. You have 8 hours in second, and the swelling rate parameter here. It's 100 times the consolidation rate. So in our experiment, we have 33 days of swelling rate. Okay, so I will try to do it. It's slightly the same as the resuspension test case, only we have just one event. One event, that means that one bottom stress event, and we cut off at 37 days. So below you have for the red point here. So it's half day, 2 day here, and 32 day here. We have the representation of the structure of the layer in the bed. And as equilibrium profile, it's updated at each time step. We have different equilibrium profile. And we can compare with the solution of the bed cohesive module. And so it's slightly the same of the previous test case. What happened here, you see that we have a loss of material. So that means that it was erosion again on the fluid, on the column of water above. And we see that there is a different profile of the critical shear stress for erosion computed in relation with the scheme. Here we see we are in this place on the right of the equilibrium profile, and that's why I put the eroded profile here. And again, 32 days later, we have the same with a loss of material because we have layers more erodible. Okay. So what happened next? So we are here, 32 days. Now we are 38 days later. We can see that we have a different critical shear stress profile here, and we are here on deposited profile, and we see also there is a layer consolidated. Yes, I don't know if you look well, but it's more consolidated on this part of the layer of sediment. And that's it. Next 32 days, I remind you the time scale was 33 days. That means that the profile reach the equilibrium profile in this way, and then reach the other part and begin to have a deposited profile, as we can see here. So we have consolidation next, next 38 days, sorry. And also we can see that when we cut off the bottom stress, we have deposition again. Yeah. Okay, so I move on now. It's another case. I didn't work on that. It's a case we initialize the linear beach slope to see what the effects of wave forcing on sediment bed. The idea here is to predict onshore and offshore sandbar migration. Also, we are using experiment data from European large installation to see if simulation of CROCO fit well with this data. There are two experiments, the 1B, so it's here on the CPPDF file on the right. 1B means for offshore case, and 1C is for accretion. So you have to switch on this flag on the onshore flag if you want to see accretion process. Okay, in this case, I will only talk about the first possibility to force this case. I will show you only the WKB wave model possibility, but there is also in non-hydrostatic mode we can use wave maker for wave resolving simulation. You need high resolution at the bottom, but here I only talk about the first part, so it's a wave average solution. So you use this wave model and we initialize the BBL, bottom boundary layer, and process then wave current interaction. So this is on the right, on the top. You see, as Rashid show you also, you see the slope linear beach. It's here, and we were using yes, it's 200 meter with resolution of 0.25, and that's it. For the dynamic, you are using morphodynamic also. And then WKB, it's for wave propagation model. So it gives you monochromatic waves given by the name list on CROCO on the WKB here wave section. So you give the peak period, but also the wave amplitude or the wave height of your forcing, and then it is variable to another routine. So I won't explain more because Rashid did that, but okay, it passes this variable to BBL routine, and there is an interaction between the interaction between current also. And I invite you to see much more the presentation of Rashid about this thematic. So for the sandbar, we have two classes of 120 or 220 micrometer with density of 2650, and it is written here, different critical shear stress. We are using SUSPLO, suspended load, bed load transport. For the bed load formulation, we use a Vandera. So you can see with the CPP key bed load Vandera. We are using bed load coef here. So it multiplies the bed load by 0.5. And we use here for 1 hour simulation a factor of 18 here. That means we have the result with morphological bed 18 hour later. This is for the 1B case. For the 1C case, we are using the 13 value, 13 for Morvan. So at T0, we initialize with beach profile with linear slope. Next, we have different cases. So as I said, it was 1B and 1C, but at the beginning, we are using the 1B. So in dot line, we have the initialization here. In solid line and black line, we have the result from CROCO. And in red, we have the data. So intuitively, we see that we have moving of transport of sediment here. We have a migration of Sandbar here. In this case, yeah, and sorry, I forgot to talk about that. In this case of 1B, we are using different parameter. So we have height, significant wave height of 0.45 meter, peak period 5 seconds. It is it forces the model at the western boundary here, and you will have on the different experiment case other result, because here you see that we are using different wave parameter. That means that here we are using high energy waves, and for the 1C, here we are using low energy waves. I put another number here. It's more or less a theory that gives you an idea of what happened. It's a Dune number. It's a ratio between the significant wave height, peak period, and settling velocity. The settling velocity don't change anyway. But this number gives you an idea which is predominant between erosion and accretion. So you can see here it's positive. So the theory told us that we have erosion process are taking place here, and the other one, if you are looking here on the next case here, we see contrarily, we have a migration of the Sandbar in the other way on onshore, and we have accretion here. So on the first experiment, we have erosion, and the next one is accretion. In more detail, we can see here comparison between flume data. So it fits well with what means square wave height here in this experiment. And finally, we see that it fits well with the erosion theory of Dune because of you have more bottom concentration here, and also the model fit well, and is anti-correlated with the undertow. Okay, so I said I didn't present anything about Mustang, but finally, okay, I go quickly. Here it's only just to see the response of a mud bed with several tidal six forcing. So what happened here, if we have a flat bottom on the boundary, we've only give a pulse of on SSH like this. So it is extracted from the routine, and we have here, so we are using two non-cohesive sediment, 200 micrometer and 100 micrometer. And as we can see, so it's a Hofmöller representing the velocity, barotropic velocity, and below we have the concentration, and we can see that there is an anti-correlation between the velocity and the concentration, and when your velocity going westward, your concentration on the column will be greater. So it is an example from Mustang. So finally, this is a recap of what we have on the CROCO framework. So I talk about Sandbar, but there is also planar beach and RIP test case. There is in this column the CPP key. When I say no, it means that the CPP key of sediment is not activated by default. And which model it is used for. So you can see about all these test cases that there is some work to do for instance test with another model. We have also I didn't talk about that, but there are the process of flocculation. It is not on the implemented yet, and there is also a realistic case here from Guilaume, but it is done with Mustang. So it's like a recap. If you want to add a line to this table, you can build your own test case. You can go to the literature, create your own CPP key, and give various analytical field, and put on different files, CPPDF, and agreed, and initial analytical routine from CROCO. And you can adapt sediment name list also for USGS, but also Mustang as you want. Voilà. So to me, that's the end. Andrés?
Sí. Sí, disculpa. Questions? Let me see just in the chat. No. Okay, if there are questions, we will see this we will do a tutorial in the afternoon with some of these test cases. So thank you very much, Guilaume. Thank you, Rashid. And we will see how easy it is to run the models, how fast they are, but I guess now comes the adaptation to your own case. And well, let's see let's learn how to use the test cases in the afternoon. So I will stop the transmission.